All right. So last time, of course, we had completed the soda ash process. We also mentioned that from the Leblanc process, one got chlorine subsequently, but that wasn't possible with the Solvay process. So there was always this issue of so what are we going to do about getting chlorine? And also, people required a stronger alkali. Soda ash was fine, but people required something like sodium hydroxide, which is a much stronger alkali. Of course, we've seen that you can convert sodium carbonate into sodium hydroxide by reacting it with lime. That can be done, and that was being done. But the chlorine issue was still a major concern. At that time, of course, not really only for this, but people were working on molten salts and doing electrolysis. So people knew that you can electrolyze salts, provided you can make them ionically conducting and in the molten state. But then, molten salt means it gets quite complicated because some salts are not so easy to melt. It's not like melting tin. Okay? So people were looking at, I mean, how do we really solve this problem in a solution mode? I mean, can you do electrolysis in solution and try to get chlorine? Because chlorine was the greater interest. Remember that by that time the important role of chlorine as a disinfectant. I'm not even talking about chlorine-based organic compounds, but I'm talking about as a disinfectant was so well known, and God knows how many lives were saved because of chlorine. So there was a huge interest in chlorine. So people were of course interested in chlorine and wanted to get chlorine, but they didn't want to do molten state electrolysis. So the interest was to do it in solution, but there were issues, and we will discuss what some of those issues are. Now, obviously, you will require power to conduct the electrolysis because it's a non-spontaneous process. The chloride to chlorine, you can see the half cell potential is minus 1.36 volt. Again, if you have to get OH minus, okay, then the half cell potential is minus 0.83. So if you add these two up, it comes to minus 2.19. Assumption was that in the anode, you'll oxidize chloride to chlorine. And in the cathode, of course, you have to reduce something because it's going to be in water. So the thing that will be reduced most readily will be hydrogen ions. Although in alkaline conditions, there'll be very little, and that actually adds roughly about 59 millivolt per pH. That's the penalty. But you can get hydrogen because there is water. And then once you have got hydrogen, then of course only the OH minus will remain from water. And so you have got, and the chloride has gone off as chlorine. So effectively, you would get NaOH. That was really the broad concept of how it's going to be done. Now, and the first such attempt was in this cell. It's known as the Hargreaves-Bird cell. But we know that if chlorine is being generated and also at the same time you're forming hydroxyl ion, then of course there's a very serious issue because it will react with the chlorine and it will form hypochlorite. So you may lose the chlorine unless of course your intention is to make hypochlorite. But otherwise there is an issue. So at that time people had the smart idea that let us divide the cell, partition it so that the anodic half cell and the cathodic half cell are kind of segregated. So they had an anode. Carbon was the anode, and the cathode was a copper gauze which they had taken. Now, what this diaphragm was meant to do was that it was, I mean, the idea was that the chlorine that is being generated should not pass over and react with the hydroxyl ion. So that was one. Conversely, the hydroxyl ion, which was being generated, should not pass over to the anodic compartment and generate hypochlorite. So that was the idea. So they made a diaphragm. Now the diaphragm was reasonably good at preventing the chlorine from moving over from the anode to the cathode, but it wasn't really so good at suppressing the migration of hydroxyl ion from the cathode to the anode. That's where they had an ingenious idea. What they said is, or they tried it out. I don't know if probably it was just based on experimentation. They said that hydroxyl ion seems to have very fast transport across the diaphragm. Now, would that also be true? For example, if you had different anions, like if you had sulfate anion or carbonate anion, so they probably wanted to do a study to see what happens with other anions, and how those transport. And somebody had the smart idea that if we bubble carbon dioxide through hydroxide, after all, what will happen? What will form when carbon dioxide reacts with hydroxide?
Bicarbonate.
Bicarbonate or carbonate, absolutely. So what they did is they started passing carbon dioxide and effectively ended up forming carbonate. Of course, it required some temperature to complete the reaction. So they were not only passing carbon dioxide, but they were also passing steam, to heat up the solution. And they found, very nicely the hydroxide gets converted into carbonate. And the wonderful thing was that carbonate passage through the diaphragm was very, very minuscule. So effectively, what happened was that in the anode, they converted chloride to chlorine. In the cathode, H plus became hydrogen, so you generated OH minus. The interesting thing was that the sodium ions from the anodic compartment, they could migrate towards the cathode. There was no problem with that. But the carbonate, the carbonate did not migrate from the cathode to the anode. So the sodium ion, which was left over in the anode compartment after chloride had been converted to chlorine, that migrated to the cathode, and you had carbonate being formed from the hydroxide, and therefore you ended up forming sodium carbonate. So the beauty was actually people were quite happy with the Solvay process and soda ash, but they couldn't get chlorine. So now you had a system where one could get soda ash plus chlorine, but then it really could not compete with the Solvay process, because it was so well entrenched, and it was so cost effective to make soda ash in that way. And I mean, it is stupid in a way that I am using so much of energy to make what could have been a much more powerful alkali, which is sodium hydroxide, and then I'm just passing carbon dioxide and forming carbonate. It's like I'm reducing its potency, right? And yet I invested all that power, so it didn't make sense. But then I think that it's important that you understand that there is a trajectory of technology development. Nobody waits for utopia that, oh, I'll have this grand process where I'll be able to do it. Whatever in the interim seems smart, you implement it. Okay, you don't have to waste your time. I need chlorine here, I'm getting chlorine. So fine. It's not the greatest solution, but it's a pretty good solution. Okay, and I think that that's the kind of spirit with which you must all of chemical technology has progressed. Nobody has waited for the ultimate solution. Ultimate solutions have come, but they've come subsequently. Okay, but you didn't wait for that. So what you can see is that they were just filling up the anode compartment with saturated brine. And then, as I told you, when the chloride was getting converted into chlorine, the sodium ion and the water, they were basically moving into the cathode compartment, and there the water was getting reduced to hydrogen and OH minus. You form sodium hydroxide, but then there was a back migration of the hydroxide, so they were purging carbon dioxide through the cathodic compartment, and that formed carbonate. And so I ended up, those were my two products, sodium carbonate and chlorine. See, this is again very interesting. People said, yeah, but diaphragm, is not so good. Now, is there any other way in which I might be able to suppress the back migration of hydroxyl ion from the cathode compartment to the anode? It's important. So now this was a wonderful engineering solution. What they said is that why don't we also create, apart from having the diaphragm, which does a so-so job, not a great job, but take at least something it does. But can we also introduce a hydraulic gradient? So effectively what they did was that they made the cell sloping. So they created a hydraulic gradient. Where is the hydroxyl being formed? In which compartment?
So cathode compartment.
Cathode compartment, right? So you put the cathode compartment sloping down and you keep the anode compartment going up. And why? Because in any case, that's what we are doing in the Hargreaves-Bird cell. I mean, the sodium ion and the water were basically passing through the cathode. They didn't want to suppress that. That was fine. But because they created the hydraulic gradient, so what happened was now there was another pathway through which I could inhibit, the back migration of hydroxyl from the cathode to the anode. You can see how smart a solution it is. And of course, that's not the only reason. There were many improvements made on the membrane so that the inherent ability of the membrane to better block off the hydroxide was there. I mean, there were improvements,
So
no
sorry to
denying.
interrupt you, so but
Yeah,
can you repeat the last part, sir? Can you repeat this innovation?
yeah. So what happened was you can see that this thing is sloping, right? This cell, all right? So what happens is the natural gradient is from the anode to the cathode, not from the cathode to the anode. Is that clear? Okay.
Yes, sir.
So if I'm forming hydroxyl here, the tendency for back migration will reduce because I have got a positive hydraulic gradient from the anode to the cathode. Clear now?
Yes, sir.
What a brilliant solution. But then, let me also tell you that there were problems. It's not as if all the chloride was becoming chlorine. Like it's not as if I put 30 grams of sodium chloride into my solution in a liter and all of it becomes chlorine. It doesn't happen. There will always be a certain amount which will remain unreacted. Second, because they wanted to really submerge the cathode with a flow from the anode. So obviously what that meant is that they had to increase the flow rate from the anode to the cathode, and that made it even more difficult to convert all of the chloride into chlorine. And so what is the penalty that one would pay because of that? Chloride was unreacted. Well, at the point that I'm trying to recover sodium hydroxide from the cathodic stream, obviously that sodium chloride will be a contaminant. So I'll have to make sure that I am able to remove it. Otherwise, I'll have sodium hydroxide laced with sodium chloride. People may not want that. So obviously there were complications that were introduced downstream which would involve a better separation process to remove sodium chloride from sodium hydroxide. But what they said is that is a lesser price to pay compared to the back migration of the hydroxyl ion. Is that clear? The compromise?
So even here, was CO2 being passed for further
No,
cleaning?
no, it was to prevent. You see, because now I wanted to make sodium hydroxide. People said, I don't want to make sodium carbonate. I can get that from the solvent process. Why should I make sodium carbonate by this? I only want to make sodium hydroxide, and it was basically to suppress the back migration. That was the only reason why I was bubbling CO2 and converting it to carbonate to inhibit. But somebody had the smart idea that introduce a hydraulic gradient. Is that clear?
Yes, sir.
Okay. So hydraulic gradient was introduced to not need CO2 bubbling. So effectively now what happened was that in the cathode compartment, I ended up forming NaOH with NaCl in a solution form. And in the anode compartment, I was generating chlorine. And chlorine did not pass through the diaphragm. That was one of the nice things, about the diaphragm, that even with the hydraulic gradient, it did not allow the chlorine to pass. So the chlorine went off. Now, another big problem with this hydraulic gradient, one is that there is an NaCl contamination. The other is because I'm having a high flow rate of my sodium chloride. So what happens is that the NaOH which was formed was relatively more dilute. So what it meant is that the evaporation load to strip off water and also to get rid of my sodium chloride obviously was a more energy intensive task. So I had a greater evaporation load as well as a purification load. Both of them were there. But that is really the diaphragm process which was practiced for years and years. Even I will tell you, even in 2000 and what 2005, 10 or something, I remember going to Tata Chemicals and they had a diaphragm cell. That's what they were using to make caustic soda chlorine. So it was a very well practiced technology. The second thing that you need to understand is how people came up with wonderful breakthroughs. You see, I'm getting chlorine. That's fine. Okay, I'm getting chlorine, but chlorine is a gas. We will need to transport chlorine, and it's not so easy to do. And what you see, the linking. Someone said, "Hey, why don't I put it in high pressure tanks?" And people knew about the liquefaction temperature of chlorine, and people said, "I can make liquid chlorine." You know, but then when they put that in those tanks, they found the tanks are getting corroded because of chlorine. And then again, someone obviously did great work, and it was BASF who did this work. You know, very smart thinking. BASF just must have said, "Hey, we are in the sulfuric acid business. For the contact process, we have been drying air with sulfuric acid. Why don't I try to see if chlorine can be dried with sulfuric acid? Because the chlorine that is coming out here is wet. It's coming out from an aqueous system. As the chlorine is coming out, there will be entrained water, which will come out along with the gushing chlorine. So they had to remove that water, moisture, and it worked beautifully. They were able to take concentrated sulfuric acid and dry chlorine, and after that compress it and liquefy it, and then when they put it in stainless steel containers, they found it's perfectly stable. So a huge problem was solved. That now people had a way of being able to make liquefied chlorine, which made its transportation so easy. And even to this day, all of us practice that. All the chlorine goes in that manner. Here, of course, they had to carry out the evaporation and purification. The sodium hydroxide has a high solubility, and sodium chloride solubility doesn't change at all with temperature. So as they were evaporating the water and making the sodium hydroxide concentrated, the sodium chloride was falling off, and that's how they ended up making a relatively pure sodium hydroxide, but obviously it was still quite contaminated. This is another very important thing that you need to understand when you are talking about a process. Look upstream, look downstream. At the end of it, what am I trying to sell? I'm trying to sell a saleable sodium hydroxide. I cannot sell that dilute sodium hydroxide as I get it from the cell, from my electrolytic cell. So I have to obviously factor in the cost of doing it. And I must also understand many things around how to concentrate, etc. Likewise for chlorine, I have to factor in what is my cost of drying, compressing, etc. Cooling the chlorine. I have to do all that, factor in all these costs. It therefore becomes also important for us to understand, because what am I trying to do? I am trying to convert liquid solution of sodium hydroxide. I'm even ignoring the sodium chloride, and let's say I'm trying to make caustic lye. I have to understand, is it a very simple process? If you're ignorant, yes, it will be a very simple process. You will think, hey, let me keep evaporating water. Somebody says, ye alkaline thing hai, let us try to do a vacuum distillation and try to remove the water. But the problem is that if you look at the phase diagram of sodium hydroxide with different amounts of water, so what you find is that it is highly complicated. This end over here is, suppose I want to make caustic lye. This is sodium hydroxide, pure sodium hydroxide. Now, at this point, I get sodium hydroxide with 1H2O. Here I get sodium hydroxide with 2H2O, and it goes on this way. So I'm starting from here. If, let's say, I try to do a stripping operation at a relatively low temperature, suppose let's say 50 degrees centigrade, and I did not know all this. So I'll be able to go, let's say I'm evaporating and I'm going in this direction, I'm maintaining the temperature. What will I hit? I'll hit this particular part of the phase diagram. And what will happen if I try to evaporate more? I'll just get NaOH, H2O. I won't get, doesn't matter how much I try to evaporate and remove water, it's not going to happen. What will come out is NaOH, H2O. So I have to know that, if I want to get into this part, obviously then I have to make sure that I am at a temperature of around at least 90 to 100 degrees centigrade. And then I have to look at the thermal stability issues, etc. And then if I touch this, I would have touched the part of the phase diagram which will enable me to make a pure caustic lye, which is free of water. So please remember, I just wanted to illustrate with a phase diagram that all of these and where all these phase diagrams, etc., become relevant. Are all of you familiar with the phase diagram or the equation? Have any of you seen this equation? Are you familiar with it? F is equal to C minus P plus 2.
Yes.
Okay. So you know that F is your degree of freedom. C is the number of components. In this particular case, the number of components will be 2, water and sodium hydroxide. Then you'll have to see number of phases, because each of these solids is a different phase. I might form ice. I can form NaOH with different numbers of water. Each one will be a separate phase, and then I can have a solution phase. So I need to understand the phases. And then suppose I am doing it at varying the temperature. So I'm keeping temperature as a variable. but I'm doing it at constant pressure because earlier days people really did not change pressure too much because it required sophisticated equipment. So if I rewrite the equation, F is equal to C minus P plus 1. Okay, so that's just to show you, and then factor in these kinds of energy requirements so that you get an overall picture of what is the energy involved. There's a reason why I'm telling you, and that will become clearer as I go along. We've talked about some of the weaknesses of the diaphragm process, right? What were those weaknesses which we talked about? What were the problems?
NaCl contaminant.
Very good. Great. NaCl contamination.
So lower production of chlorine.
I think that's a very smart, good point. Lower production of chlorine than desirable. I'm putting that. What else? What were the other problems?
Dilute NaOH is formed.
Very good. Excessive evaporation flow, right? This is again something so interesting. You make a note of what are the drawbacks and then don't bother about whether you can solve it or not. Nothing prevents you from at least thinking about a solution. Whether you'll be able to come up with a solution or not, that's a different matter. So, but people realized and they said, we must try to improve the process so that these problems are overcome. Can you think of any other way of doing the electrolysis? Any variant?
Excuse me, sir. Sir, in the NaCl and water mixture, so
Yeah.
can we add more amounts of chlorine other than NaCl so that the chlorine concentration increases in overall?
If your objective is to get chlorine only, then of course what you're saying is correct. I can vary the salt. I might be able to get something else. But the objective was also to get sodium hydroxide. So then I can't do something else. Is that clear?
Okay, sir. Yes.
Any other thing that comes to your mind? And keeping specifically these. NaCl contamination, lower production of chlorine, and excessive evaporation load. Is there any other solution that you can think of? I mean, it could be a dream. It could be a wish. You'll find that, yes, it was solved, but it was solved with a penalty. There was a price to pay. It wasn't that there was no price. Sometimes people can think really out of the box. Two things were connected up in coming up with this technology. One was people were aware of molten salt electrolysis. When I do molten salt electrolysis, what would I get? What would I get at the cathode? At the anode, I'll still get chlorine. At the cathode, what will I get?
Sodium. Solid. Sodium.
Very good, sodium. Molten salt electrolysis will give sodium at cathode. Okay, and I'll get chlorine. What's the price that I pay? What is the price? And don't forget, I can take sodium metal and I can add it into water and I'll get sodium hydroxide, right? And hydrogen will come out. And that's the hydrogen which I get in any case when I do chlor-alkali process. I'm getting sodium hydroxide, I'm getting chlorine. But what is the price?
Sir, energy to melt salt.
Very good. Price, energy to melt salt. What else?
Different equipment will be required.
different equipment. Huh? Yeah, okay. Different equipment. What else? What was I reducing in the other one? In the conventional chlor-alkali process, diaphragm one?
So the H ions.
Right, to form hydrogen, right? Here, what do I have to reduce?
So sodium ions.
Correct. Which would be harder to reduce?
Sodium ions.
Absolutely. So there would be a large potential for sodium ion reduction. Okay, so these are the price what you pay, but probably the issue of electricity was severe, but at that point they wanted a solution. Okay? Now, so that was one. At least people were aware that in molten salt electrolysis, I can get sodium metal, and then once I've got sodium metal, I don't have any NaCl, NaCl, nothing. I can just put it into water, and I can put it into the smallest amount of water, and I can make sodium hydroxide, and there's no issue. And if I take just the right amount of water, I can actually make sodium hydroxide absolutely solid sodium hydroxide with zero water and liberate hydrogen. That's what I can do. So people would have said, "Hey, why don't we try something like this?" Okay, and but only the brilliance is, I'm not going to do it in the molten state. Question: can I reduce sodium ion to sodium metal in aqueous system? Possible or not possible?
So possible, sir.
How?
So changing the concentrations.
So can somehow we can restrict the H plus ions going to the
Restrict
cathode.
the
H plus ions going to cathode.
So use a selective electrode which only
brilliant. Now, around that time, what happened was that this person, in fact, he also got the Nobel Prize, uh, and he's known as what is called the father of polarography. He was playing around with other types of non-conventional types of electrodes, and in particular, what he said is, it does an electrode have to be always a solid? Does an electrode have to be always a solid?
No, sir.
What is this liquid?
Mercury, sir.
Absolutely, you can see it over here, but you may have thought of it even otherwise. I mean, for that matter, just like we talked about tin, I can take molten tin, right? It would be a liquid. Any kind of low melting metal, I can have a liquid. So what he was doing was that he created what is known as a dropping mercury electrode, and the reason for that was he recognized, that what happens is that if the surface of an electrode gets contaminated, then of course it will interfere with all your redox processes. And so he thought that by continuously dropping mercury, every time I'm making a fresh surface area. And so you could get probably the most precise values of redox potentials, etc. Because of that, because there was no interference from other impurities which might otherwise start lodging in your electrode if I don't have a regenerable surface. So Hedowski became famous for polarography. Okay, someone somewhere would have said, "Hey, can we try and use mercury as the cathode for my chlor-alkali process?" What would happen? I mean, and I'm sure that's the way these people used to do things. They were probably not very sure of what will happen. but it didn't prevent them from trying it out. And I hope you can see also how knowledge gets created. So they tried it, and you know what they found? That in fact, what one of you asked the right question, that can I prevent H plus at cathode, right? One of you asked this question or not?
Yes, sir.
So what they did is, what they found, there's no need to prevent it. But the electrode prevents the reduction of H plus to hydrogen, and it has a very high over potential for the reduction. I didn't have to do anything. I just had to take mercury, and so much so, the over potential is so high that the H plus is not reduced, and I can keep biasing my cathode more and more negative till I hit the reduction potential of sodium, which is minus 1.85 volt. Now you can see what is the normal potential, minus 0.83 volt for water going to hydrogen, and this is 1 volt further to the negative. And even with 1 volt further to the negative bias, even then the mercury rejects the H plus and doesn't allow its reduction. More interestingly, it does another thing. It allows the sodium ion to get converted into sodium, and after that, what it says is, hey, I will wrap myself around you and I will not expose you to water. And so it basically formed an amalgam with sodium. Great things. Over potential with Hg high enough to reduce sodium ion instead of water. Okay, that's one. And unique property of forming an amalgam. So imagine there is sodium there, but it's still not reacting with water. What a remarkable thing. What is the price that I paid? I had to carry out my electrolysis at a much higher overall cell potential. Here it was minus 2.19 and here it is minus 3.2. So I paid a price, no question about it. But someone said, look, once I have got my amalgam, I can separate out my liquid amalgam, and I don't have any sodium chloride, I don't have water, any contamination of any kind. They said, now can I release the sodium hydroxide from that sodium? A systematic study was done, and what they found is that you can play this game of forming an amalgam with of mercury and sodium, but with a limited quantity of sodium. Once it exceeds a certain amount of sodium, then of course it's not going to form an amalgam. It may still reduce the sodium ion, it may still have a high over potential for the H plus, but the sodium will probably get reduced and instantaneously react with water. So they figured out the concentration up to which the sodium can be incorporated in mercury. I hope you can see how science and analysis and everything fits in so beautifully with technology. And then what they developed, the Britishers, is what is known as the Kastner-Kellner cell. 1897, they were given their patents. So it was after the Solvay process, of course, was invented. Now, what these people did, very smart guys, they said they made a rocking type of a cell. So what happened was that, I in one place, I carried out my electrolysis with mercury and graphite. Okay. Later on, of course, it was changed to something else. So anode was graphite. They formed chlorine, and in the cathode they formed the sodium mercury amalgam. Moment they had got enough of the sodium, what they did was, it's a rocking type of thing. So they tilted the cell, and it went into another cell. Now, in this particular cell, this is a denuding cell. In other words, they had to expose the sodium again. And now what they did was the mercury sodium, which was my cathode, now they used it as an anode. And they used some other thing as a cathode. Yeah, iron or nickel or something else. Okay. And so they were applying a positive potential to this, and so under those conditions the sodium got released as sodium ion. So this amalgamation property was only relevant under very, very strongly negative bias. So under a positive bias, the sodium got released as sodium ion, and in the cathode I ended up again like before forming hydrogen, and so I had OH minus, and my sodium ion and OH minus became sodium hydroxide. Now, because I don't have any NaCl, nothing, I can take this in the smallest amount of water so that I make an extremely concentrated sodium hydroxide solution, and I can also make it very pure because there's no contaminant around. All the contaminants are left behind in the cell. And then, I keep playing this game, back and forth, rocking of the cell, and I complete my process. So two separate cells. This actually was being practiced even in Europe. Till about 2011-12, But what happened was that people discovered that when I'm doing an oxidation, some amount of mercury also gets oxidized and dissolves. So there was a problem of mercury poisoning, which came to be known as the Minamata disease. Minamata and Nigata were the two people who basically found this. They said there's a serious problem, and people were dying. And so, although they had solved every other problem, it is one of the most beautiful technologies that you can imagine. But because in the denuding process, some amount of mercury was getting dissolved and creating this Minamata disease, and it was a sludge which was very difficult to deal with. So they had to slowly, over a period of time, more between say 2000 and I will say 5 to 5 onward, gradually the mercury cell process slowly began to die. But nobody wanted to go back to the diaphragm process, and so another process was invented.
So
Yeah.
so sorry to interrupt you, but can you explain the working of this in brief once again?
Yeah. So in the first cell, what I have is that my chloride ion at the anode is becoming chlorine, right, as before.
Yes, sir.
Okay. And at the cathode, the mercury, this is you can see this electrode dipping in this thing. This
Yes,
is
sir.
actually liquid mercury. Okay. Right?
Yes,
This
sir.
stuff is dipping in this. So when this is my cathode, so when it is getting negatively biased, my sodium ion which remained is now becoming sodium mercury amalgam. Is that clear?
Yes, sir.
Now what I'm doing is I'm rocking this, and it is coming into the middle compartment over here. Now in this compartment, what I do is this stuff, okay, which is my sodium mercury amalgam, is my anode, and it is getting oxidized. The oxidation that is taking place is that the sodium is getting released as sodium ion, and in the cathode, my H plus is getting reduced to hydrogen. So I'm ending up forming sodium hydroxide here. Is it clear?
Yes, sir.
So that's the process. And by the way, today there is a more advanced version of this same cell. This basically is not very different, except what they do is they pump these amalgam. So this is the process where I am generating chlorine. Now, they also realize one thing. Earlier, they were using graphite as the electrode. Problem is, if I want to write in the graphite, chloride is going to chlorine, that's great. You are welcome to write it. But there's nothing preventing some of the carbon also getting oxidized to carbon dioxide in the presence of water. It can happen. And that's exactly what was happening. And so the carbon was gradually becoming thinner and thinner, and the cell resistance was increasing because of that. And so the electrode was not dimensionally stable. Then some people discovered, this person Beer, around 1965, 67, long after the discovery of this process in 1897, these people they were able to make a new electrode, which had all the great properties of graphite. Means chloride could get oxidized to chlorine. The over potential, if anything, was lower than in the case of graphite, and it was dimensionally stable. Nothing happened to the electrode. So the performance of the cell day in and day out was absolutely the same. So that was the electrode. It was a titanium coated with what are known as valve metal oxides. But one of the major advances which took place in this technology. Once you have made this, it comes to the denuding cell. Effectively, it's the same thing. You can see the amalgam becomes my anode, and I have a graphite which is serving as my cathode. This is producing hydrogen, and off I'm getting hydrogen, and sodium hydroxide is being produced. And now my mercury has got free of sodium. Off it goes again to restart its work in the cell. All clear?
Yes, sir.
Let me ask you now. So great technology, but because of this disease, mercury poisoning, it had to be phased out. So what do we do now? We had the diaphragm process, we had this mercury cell process, and if you had a wish, what would you do next? What would you try to improve? What was the problem with the diaphragm process? What is the basic problem? Well, the basic problem was that the diaphragm was not really doing a great job of separation. It did some job. It blocked up the chlorine, etc. But then it was a very leaky stuff still. And so people would have said that instead of the diaphragm, if we can make a better membrane, which can do a better job than the diaphragm, it is much more selective to what specifically I need to transport and blocks up everything else, then I have no problem with the diaphragm process. Right? Understood or not understood?
Yes, sir.
Okay. Around that time, what happened was that there were two important developments that were taking place. The first was that the fuel cell was being developed for the space mission. That was one. And what was the fuel cell? So, for example, this is an anion exchange membrane, very selective, developed by DuPont. On one side, they were pumping hydrogen, and the hydrogen was getting converted into water. They were oxidizing the hydrogen and ending up with water, and it was releasing 4 electrons. On the cathode side, they were pumping oxygen. what was it doing? The oxygen was taking electrons from the anode side and getting converted into hydroxyl ion. So, hydroxyl ion being formed on one side, and on the other side, it was forming water. But then this will require hydroxyl ions, okay, to complete this whole process. So what happened was that they introduced a membrane, a polymer electrolyte membrane, which was very selective to the permeation of hydroxyl ion from the cathode side to the anode side. So over here, I just supplied the hydroxyl ion and I could convert this into water, and so there was no problem. So effectively my input was that I was pumping oxygen and I was pumping hydrogen, and I was also introducing water because I'm depleting this place in water, so I have to put in some water, okay, into the system. That was what was being used in the spacecrafts to provide the power, from hydrogen and oxygen. They said this is great. If we can do something like this for the chlor-alkali process, that would be nice. There were two things. One was, and we'll see later on, that one, they had to not take an anion exchange membrane. What they realized is for the chlor-alkali process, they would require a cation exchange membrane, because you remember in the anode, I've oxidized chloride to chlorine. I'm left with the sodium ion, and in the cathode, I'm forming hydrogen and I'm forming OH minus. So I want the sodium ion to migrate from my anode compartment to the cathode compartment. I don't want anything else to migrate. I only want the sodium ion to go. Nothing else like hydroxyl ion moving one way or the other. No. Only sodium ion must transport across the membrane. So I needed a very selective cation exchange membrane. Second is that, you see, in the chlor-alkali cell, it's a far more complicated problem than, let's say, this fuel cell. Why? Can someone tell me why? What's the complication? What is something that can be quite destructive if you're not careful? The chlorine. Okay? Because you're forming chlorine. And you know how reactive chlorine is. I mean, it will just chew up these membranes. Okay, it won't survive. At that time, what happened was that DuPont were ideally placed, because DuPont are the people who invented Teflon. And look at their thinking. They realized that Teflon is inert to chlorine. But Teflon is a neutral polymer. So someone had the smart idea that is it possible to introduce some negative groups, like anionic groups, so that it can serve as a cation exchange membrane, and I might be able to pass sodium ion. And so they started looking at sulfonation chemistry and how to make sulfonated Teflon, which can then serve as a cation exchange membrane.
So please should you repeat the last point once again?
Yeah. So what happened was that it was very clear that if instead of a diaphragm, because diaphragm's problem is that it is not selective at all. So what they said is, let us try and replace the diaphragm with a proper membrane and a cation exchange membrane, which will only allow sodium ions to pass across the membrane. And the sodium ion will pass from the anodic compartment to the cathodic compartment. Because it's in the cathodic compartment that I am forming hydroxyl ion when H plus is going off as hydrogen. And in the anodic compartment, I am being left with sodium ion. So I just want the sodium ion to pass from my anode to the cathode. I don't want hydroxyl ion to pass from my cathode to anode, because then it will react with my chlorine and form hypochlorite. So I need a selective permeation of only my cation, and the cation that I'm talking about is sodium ion. That's what has to pass. So that's effectively what they did. Second, because in the anode I'm forming chlorine, and the membrane will see the chlorine because as it is getting evolved. So if the chlorine comes and attacks an organic polymer, most polymers will degrade in the presence of chlorine. So they had to solve this problem. What DuPont realized is that they are better placed than anyone else to solve this problem because they had invented Teflon. And Teflon was shown to be resistant to chlorine. But Teflon is just CF2 polymer, polytetrafluoroethylene. So someone said, if we can introduce, in place of one of the fluorides, suppose we can introduce a charged group like a sulfonate, then my counter ion can be sodium ion, and then it would become like a cation exchange membrane. So I might be able to make an improvement over the diaphragm process. Is that clear?
Yes, sir.
Yes,
Okay.
sir. Yes, sir.
Okay. By the way, just to show you, today, in fact, all of the entire alkali production in the world, almost all, okay, is now done with what is known as the membrane technology. I've just shown you a plant, these people, it's in Asahi, they develop their own membrane. Many companies subsequently develop their own membranes, although credit must go to DuPont because they were the pioneers in developing these membranes. You can see, like for example, there are 130 plants just from this company Asahi, the licensed technology, and 25 million tons of caustic soda is being produced, from this. I hope you can understand how revolutionary these things are. So let us try and understand now quickly what we are saying. I'll just show you schematically so that it's clear to you. So what did he do? What did DuPont do? DuPont just replaced the diaphragm with this kind of a tetrafluoroethylene, Teflon modified membrane. So that's what they have. This is this membrane. What am I doing in my anode? I'm converting chloride to chlorine and I'm being left with sodium ion. And what am I doing in my cathode? As before, I'm converting H plus into H2. So I'm generating OH minus. Now what this membrane does is that it only allows the sodium ion to pass through this membrane, and it goes here and it becomes sodium hydroxide. So this part of my cell becomes depleted in NaCl, and this is my NaOH. Over here I don't have to take any NaCl. I've just taken water, maybe with a small amount of NaOH initially to make it ionically conducting, but it's otherwise pure water. And this part, as my sodium chloride is being depleted, I'm just taking it out. Okay, the chlorine is coming out, and the rest of it, the process is the same. That liquefaction of chlorine, that as before. And over here, what am I doing? I'm making sure that there is no chlorine that is left. So there's a dechlorinator. Then I'm passing it for brine resaturation. Where did we encounter brine resaturation? Which particular process? Dual process. You remember, the depleted filtrate was being resaturated with sodium chloride. So you just take this and you put sodium chloride, resaturate, and again make the brine saturated, and so the whole process continues. And it's all based on the fact that you could make this wonderful membrane. Now let us try and understand a little more about this membrane. What it is, you can see, is just a tetrafluoroethylene, Teflon-like thing, except there is some sulfonate groups which have been introduced. Some other company said, hey, instead of sulfonate, why don't we put a carboxylate acid group, carboxylate? So both these membranes are known. One is the perfluorosulfonate. Perfluoro means all the hydrogens have been replaced with chlorine. Okay? Because otherwise it was the hydrogen which was getting attacked by chlorine. So, and in the other case, it's perfluorocarboxylate. Now, what also they found, so very interesting when they were doing these studies, what they found is that this sulfonate thing, it has a low resistance to permeation, means that it allows ions to pass through very well. But the problem was that it was less selective for the selective sodium ion transport. Now, in this particular case, they found that the flux was very poor, means the permeation rate was very poor. So that was a disadvantage, but it was very selective to sodium ion transport. So what then they did was they had the brilliant idea that they made the bulk of the membrane, out of this stuff, okay, so that there would be a low resistance to permeation. And at the end, at the two sides, they put in the carboxylate so that this one will give you the high selectivity of permeation. So they were able to marry the properties of the perfluorosulfonate and the perfluorocarboxylate type of ion exchange membranes, and they achieved excellent permeation coupled with excellent selectivity. So this is how people come up with brilliant ideas, brilliant technologies. Mind you, there were other very, very important things that were done. I've glossed over that. Like in the previous case, they switched over to dimensionally stable anode, so that that really improved the cell performance. And in the cathode, what they found is that nickel is the best catalyst to use, because we know nickel, for example, is used in hydrogenation processes. So nickel is one of those you would expect to serve as an excellent catalyst, as an excellent electrode for H+ reduction to hydrogen. They have made some changes also in the electrode, and this is the process technology that is practiced worldwide today. Okay, so I hope you now understand the chlor-alkali process and what is the current status of the chlor-alkali process. Remember, membranes always have a problem. It doesn't matter what. One is that these Nafion type of membranes are horrendously costly. If the membrane goes bad, to replace the membrane is very, very costly. I remember there was a company, I think it was the Sriram Chemicals Group, a long time back, I think 2004 or 5, they came to us and all their membranes had got spoiled, because our institute was well known for membrane. They asked us that, can you help us? And one of my colleagues, Dr. Ramachandraya, was able to regenerate all those membranes, by just giving some clever treatments. That then became a big thing, because they could drastically reduce the cost of buying new membranes. And if they start fouling up, okay, they will their performance will go down. Now, let me ask you, in this system, can you see anything that can possibly foul up the membrane? Anything? Think hard.
Brine.
Brilliant. And what in brine?
Sodium chloride solution concentrate.
Sodium chloride, so it's you are using.
The magnesium salts.
Correct. Why only magnesium? Maybe calcium also, right?
Yes, sir, but so
Yes, sir.
calcium salts come out before NaCl and magnesium.
Array, what you are talking about out, all of it comes out. There's always some left, right?
Yes, sir.
And that is not good enough. Now, this is another thing that remember in industrial engineering, that many times what you consider pure could be terribly impure. Even with our technologies of recrystallization and everything that I showed you, we still had ppm levels of magnesium, calcium, right?
Yes, sir.
Yes, sir.
Yeah, so it's not good enough. It's a cation exchange membrane. So what will happen, and don't forget, a multivalent ion will always have a stronger interaction than a monovalent ion. Just a Coulombic interaction. Electrostatic interactions will be much stronger. So if, let's say, my magnesium and calcium ions get into this membrane, it will just go there and it will not let the sodium ion get in now. It will not want to be released. It will just sit there. So the purity of the brine in this technology has got to be unbelievably high. So that's the problem. The fouling, this is the foulant. The foulant from the brine. Once they recognized it, there was intense activity. When something is at a ppm level, what kind of treatment would you like to give to try and reduce the impurities? What could be possible ways of treatment? Remember, I'm not going from percent to ppm. I'm going from ppm to ppb.
So chromatographic separation.
Chromatography could be very good. It's a possibility. I'll just put purify brine. How? Okay, terrible English, but don't worry. Chromatography. Okay.
So can we use crown ethers for the cations?
Crown ether. Again, you'll have to look at selectivity. Well, let's put it down. Remember all these things, many things which work. When, like, let's say, suppose I've got one normal magnesium concentration, I might be able to make it 0.1 normal or 0.1 molar, and I might be able to take out quite a bit. But when I am to look at selectivity from making something which is already low to very, very low, the technologies that you require could be very different. But that's a good idea. Anything else?
So ultrafiltration.
Ultrafiltration. Good idea. Again, you'll have to look at whether you can do it with that level of selectivity. Okay.
Yes, sir.
Even in RO, let me tell you that when you do RO, okay, and forget about ultrafiltration, even reverse osmosis, you'll be left with about 20-30 ppm of solute, in your solution, and some of it will be magnesium calcium. Okay.
Sir, could you please repeat why crown ethers would? What are the disadvantages?
No. I'm just saying, in all of these cases, you'll have to look at the selectivity of binding. All right. I'm not saying that there is a fundamental weakness, but I'm just saying that it is possible that there could be.
Understood.
Anything else? Like chromatography, are there other techniques?
So we have ion exchange chromatography.
Brilliant! Ion exchange resins.
So in ion exchange resins, we will use zeolites, right?
Well, wait. Don't presuppose anything. One of the best ways to solve a problem is completely keep an open mind. Only thing that you should say is maybe ion exchange systems, adsorbents, and just leave it at that. And then, you can try out X and Y and Z and you'll see which one will solve your problem. But do not presuppose. Is that clear? All
Yes,
clear?
sir.
Okay. Now let me tell you the thing that actually worked. What they found is that these resins, which are aminomethyl phosphonic acid type resins, And mind you, this is not something so easy to, you can't guess it. Remember another thing, I should have mentioned this. You are trying to remove traces of impurities from a saturated brine. So you'll have to understand the selectivity ratio between sodium ion and those other things. Now is it clear to you? You can understand if I've got saturated sodium chloride, which has got 360 grams per liter of NaCl, and I've got 2 ppm of magnesium, you understand what kind of selectivity ratio is required between sodium and magnesium? Is it clear?
Yes, sir.
That's the issue. It must be so selective to your magnesium, calcium, that even with such a large presence of sodium chloride, it will still do a great job. Okay? And that's what this particular resin does. And let me tell you, and you can see saturated brine containing 1 ppm calcium. And same will be true about magnesium also. Temperature 75 degrees centigrade, pH is 10, and it brings it down from 1 ppm to 20 ppb. You understand? If you use this concentration of calcium magnesium in your brine, your membrane would be gone. You would not be able to operate the membrane even for 2 months. Forget about operating it for 5 years. Whereas once I reach these levels, I can operate my membrane over a longer duration. All clear?
Clear.
Okay. At the end of it, remember, in the chlor-alkali process, the things that you need to compare really are how much power do I require? Because your main input is power. Okay? Anything that requires more power is, you'll have to find ways of trying to reduce the power consumption. Let's just try and see what is the kind of profiles. This is the profile of cell voltage and current density. Current density is ampere per centimeter squared. It's typically given by the symbol J, and your cell voltage is V. Yeah. Why is current density important? What would happen if I operate something at a current density of 1 ampere per centimeter squared and 0.1 ampere per centimeter squared? What would be the difference? Which would be more desirable from an engineer's point of view? Higher current density, because then from the same cell, I can have a much higher throughput, right? After all, what is that current doing? That is the current which is oxidizing and reducing, right? So if I operate it at the maximum current density that is practical, then obviously, my capital cost will go down. From the same cell, I'll be able to generate more product. Clear or not?
Yes, sir.
Okay. So you've understood what is important. Problem is that whenever you try to increase current density, the electrode is saying, I cannot cope with your current density. I cannot react so fast. You can say electrode reaction, it's only it's a chemical reaction ultimately that is taking place, a transformation which has got a kinetics. There's a rate constant. I mean, if you are trying to, go beyond that rate constant, it's not going to happen. So what will happen? I'm increasing the cell voltage. I'm increasing what is known as the overpotential. It is well known that as I increase the overpotential, my current density will increase. But I'm wasting power because I'm deviating now from the thermodynamic cell potential. So that is the importance of the cell voltage and the current density. What happens is that in the diaphragm cell, firstly, limit of current density is quite low and the cell voltage increases very steeply, with your current density. Okay, in this particular case, in the diaphragm cell, and partly it is because you remember that we were trying to push this stuff very fast. Okay? Now, so this is what it is. Now, your membrane is better, okay? And you can see that it has got a lower slope over here. Mercury is the best, okay? That it has got the least slope. So what it means is that I can operate the mercury cell at higher current density without too much of compromise in terms of my cell voltage. Of course, it will increase to some extent, but not a whole lot. Okay. So for example, if I'm operating here at close to about, say, over here it is about 3.8 volt and my current density is about 0.8, and if I go to a current density of 1.2, that means I'm producing something like 35% more from the same cell. I've increased my cell voltage, but not a whole lot. Okay, maybe it's gone to 4.2 from 3.8 or so. Okay, whereas here, if I had to operate it in the membrane cell at, let's say, at a current density of 1.2, like here, I mean, you can see that it would require, in fact, a cell voltage even more than the mercury cell, even for doing the simple redox process of H plus to H2 rather than sodium ion to sodium. Okay, so I must necessarily operate the membrane cell at a relatively lower current density. Okay? What that means is that the throughput from my cells will be much lower with the membrane and the diaphragm cells as compared to the mercury cell. So apart from everything else that I'm telling you, I hope you can understand the advantage of the mercury cell. But it is no point talking and glorifying it and how great it is, how wonderful even the cell voltage versus current density response is, when in fact the big problem is that I've got mercury poisoning. So you understand that these are the issues. Obviously, the next big breakthrough will be that how to make this slope flatter. Okay, that is the next frontier, and if one of you can do it, maybe you will be one of the greatest innovators, if you can achieve that. Is that clear? Is this profile clear to everybody? Everybody understood? Current density, cell voltage, the relationship between the two, and the need to be as flat as possible with the least slope. Everybody understood?
Yes, sir.
Okay. So now let us do a quick comparison. Okay. Let's say if you are not trained in all this and some salesman comes and tries to sell you a technology and tells you, ये देखिए -4.4 volt है, हमारा तो सिर्फ -2.95 volt है. But then when you see the current density, you say your current density is only 0.4 amp per centimeter squared. I can only get 40% as much product from your cell as compared to the mercury cell. So I must do a like for like comparison. Current efficiency, not bad. All of them are good. In fact, the membrane cell is marginally today better, and that's all because of the selectivity of permeation of sodium ion. Energy consumption, what happens is if you take only electrolysis over here, you will get one kind of a picture. Whereas if you take electrolysis plus the evaporation that you need to do to produce a sodium hydroxide solution of required concentration, purity in all cases today is very good. Diaphragm cells still not that pure, but all of them chlorine purity is greater than 99%. In all cases, hydrogen purity is greater than 99.9%. Oxygen in chlorine, you can see that it is actually the least in the mercury cell process. So if this was a critical factor, then of course the mercury cell process would be the best. Again, chloride in sodium hydroxide, least in this particular case. So obviously huge advantages in this mercury cell. If somebody can somehow prevent oxidation of mercury by some means in the denuding cell, oh, that would be great. Just think about whether you can do it. I remember around 2007, I was giving a talk. There were a lot of Europeans who were also giving talks, and I asked them that what process are you following? They are supposed to be so environmentally conscious, and they said mercury process. I'm talking about around 2007-8. And I said, why? They said, because you get the highest concentration of sodium hydroxide, and the sodium hydroxide is the purest. That's why. And I said, and what about the poisoning of mercury? They said, oh, we deal with that separately. But obviously, they could not continue to deal with that separately, and they have all had to change. You have to decide for yourself what is important to you. And you must have the ability to ask questions. And so what this does is it provides a wonderful template. And so these are the kinds of questionnaires that you should prepare. And then you compare meaningfully. Otherwise, you'll be comparing apples with oranges. One more, just like in the other cases, this is what you'll get: 1 ton of chlorine and 1.13 tons of sodium hydroxide, and plus 26 kg of hydrogen, from your roughly about 1.3 tons of salt. I might ask you a question around E factor, and all of these are required products, desirable products. So all of these will go into the product category, and then you can work out your E factor. You can see also, if I ask you how much is the electricity consumption, steam consumption, etc., etc., and you can work out your total amount of power that you require in kilowatt hour for these kinds of units. We will continue with this tomorrow.